Switching essentially refers to the problem of how are network resources allocated to data that needs to be transferred obviously. Broadly, there are two classes of switching, circuit switching and packet switching, right. Virtual circuits are sort of a combination of both. They are circuits that are built up on the concept of packet switching, right. Again, those of you who have done a course in communication networks, telephony, any of that, you would know exactly what these mean. Exactly the same concepts being used over here, right. What happens in circuit switching is that I am going to establish a dedicated connection between, in this case, 03 and 11. Okay. So, in order to establish that connection, I need to have at least two traversals, right. From 03, I somehow send a packet all the way up to 11 saying I want to talk to you. 11 then responds saying okay, I am free, and goes back along this line. Now everything over there 03, 02, 01 and 11 are now dedicated to this link. Nobody else is allowed to use them. Okay. It has all that setup overhead, which basically says that once you have done this, after that comes the second part where you actually transfer the data. Okay. The good thing about it is contention free transmission. For the duration of that circuit, all the links over there are dedicated to this particular circuit. The problem is you can end up with fairly low resource utilization, and you have overhead associated with this. You basically have latency because you take some time in order to set up the circuit, right, and the bandwidth also is being used up for this circuit switching to set up the connection at least. After you have done the setting up of the connection, those connections are, the links are dedicated, therefore it's no further overheads at that point, right. This is effectively what happens when you are making a telephone call, right. You dial a certain number, it establishes a connection to that end, and then it guarantees that there is actually all the packets being, all the data being sent by you is going to reach that other end, and their responses are going to get to you. Okay. Packet switching on the other hand takes another approach. It says that I will take data and break it up into packets. This is what happens, for example, on the internet, right, and the packets can be independently transmitted to the destination, possibly along separate routes. There is really no startup time required over here because I do not need that back and forth for setting up a circuit. I just, as soon as I have data, I start sending it out, and the routing tables or whatever the routing approach that I am following will take care of finally getting it to the destination. The problem with packet switching is there is something called quality of service. A circuit switched connection guarantees a quality of service. It means that all links over there are now dedicated to your communication, nothing else is going to happen, whereas over here each packet is handled independently. Okay. There are a few variants of packet switching. One of them is called store and forward switching, right. What happens in store and forward is A is receiving a packet that it knows needs to be sent to B. It waits until it gets the entire packet, stores it locally, right, asks B if it is ready, B acknowledges saying yes, and then A sends the packet to B. Okay. In one way this is good because what is happening is A ensures that it receives the packet properly, it sends the packet to B only when B is ready to accept it. So, as and when B is ready to accept it, the entire packet should go through without any further problems. The issue is the size of this packet, right. What if the packet is quite large? A needs to store the entire packet before it can even start transmission, which means that potentially it can end up requiring large buffers. Okay. A variant of this is a slightly sort of optimistic approach to the problem, which says that as soon as A starts getting data and it knows that it is meant for B, it immediately contacts B and says I have something coming for you, shall I start sending it? Okay. B says okay, right, and A starts forwarding the data immediately. The good thing is A now needs to store only this much, not the entire packet. Okay. That sounds good to start with. The problem is now you are breaking that original packet up into some smaller units that are being sent, or at least you have started sending the data even before the entire packet came through, right? What if at some point after that B suddenly says, hey, wait a minute, I just missed a few bytes over here. A still has to store the entire packet, okay, because it's got a NAC, that is a negative acknowledgement, and it then needs to send the entire thing back, okay. So virtual cut through, the one thing it definitely reduces is the latency, because what happened in the original case over here, store and forward, is the entire packet has to come to A, only then the transmission to B even starts. There is a huge latency involved, whereas over here, as soon as the packet arrives over here, you start forwarding it, okay. It reduces latency. It may not necessarily reduce storage so much, especially if you have to have this retransmit on negative acknowledgement. Beyond that, we essentially bring in this concept of a flit, right. What we are saying is, I have a packet, but even a packet which might have been suitable for, let's say, an Ethernet packet, for example, can be up to 1500 bytes or so, right. Whereas the kind of packets that I might want to transfer when I am sending data around inside a chip, maybe I want to send smaller packets, right. So what you do is take packets and break them up into something smaller called flow control units, usually referred to as flits, okay. So a flit is essentially a fixed size small packet. You can, in principle, it's also a packet, right. What you end up with is taking the entire packet and breaking it up into a header flit, which has some control signals over here to show that it's a header, then a large number of data flits which have a different set of control bits, and finally a tail flit to show that this is the end of that packet, okay. Now potentially all that you have done is you have replaced packets with flits, but now flits are of fixed size. You don't have to worry about having different sized packets. You are always going to transfer a fixed size flit, and therefore you can do some slight optimizations to your switching and routing algorithms based on that information, right. In particular, there is something called the flit buffer switching, also called wormhole switching. Sometimes wormhole routing is also used, but switching is probably the more accurate term in this context, right. Basically what it says is, as soon as A receives a flit of data, it asks B if it's ready and sends it on, right. So effectively what is happening is that you need less data to be stored, hopefully, than store and forward, because you are now effectively buffering only the flits, right. The problem, of course, is all that you have done is you have taken some packet that you might have had and broken it down into smaller packets. So it's still packet based, right. The main advantage over here is the fact that the flit size is fixed and it is relatively small. So based on that, you get a little bit more flexibility in terms of how to store, etc. Okay, so this brings us to the last part of the principles of network on chip, at least the things required to understand it, which is something called flow control, okay. So what does flow control refer to? Essentially it's saying what happens when traffic is encountered, right. What if you are not able to send data on a link? This term over here, back pressure, right, is a very important term for you to keep in mind, because you will be using it extensively even while designing the modules that you are going to use for your project or any of the further stages. Effectively what back pressure says is, there should be some way by which, normally what I have is a communication that goes from A to B to C. What if C is blocked? It's not able to send its output anywhere, or it's not able to store its output. It needs to be able to send a buffer full signal backwards, which basically indicates to B, don't send any more data. That in turn indicates to A, don't send any more data, okay. If there is indefinite back pressure, you will start losing data, because A can't hold its data indefinitely, right. But if it has a buffer, some place where it can keep data for a little while, it might be that this block will clear, and then you can again start sending the data through, okay. So this back pressure is a very crucial component of getting complex multi-element systems to work properly together, right. how do you implement back pressure? That essentially is the concept of flow control. Okay. There are multiple ways by which we can do this. One of them is so-called ACK-NAC approach, right? The simplest way that we can think about it is something like this. I basically have A trying to talk to B, right? I send a packet and receive the ACK, then send the next data, receive the ACK, and so on. Okay, so this is the timeline. I basically send data, receive acknowledgement, send data, receive acknowledgement, and go on, right? The problem is major loss in throughput, because effectively what will happen over here, as I go down the timeline, is that this is useful, this is wasted because I am just waiting for the ACK to come through. This is useful, this is wasted, right? Wasted, or if you want to be positive, you can just say you are waiting. Right? So, your effective throughput, the bandwidth with which you can send data, has reduced considerably. The optimistic way of doing this is to say, as you can imagine, right, send data, send data, send data, send data, right, and finally this one sends an ACK, right. So, all this becomes useful and this becomes waiting, right, overhead reduced. But what happens if at some point B wanted to send back a negative acknowledgement, I did not receive a packet. Of course, what this means is that each packet has to have some ID associated with it, so that B can actually know whether it received all the packets or not, right, and then it basically sends back saying I did not receive one particular packet. Okay. So, when the NAC goes back, you then need to retransmit. Okay. So, this whole business of how big of a buffer should A keep, what should it keep track of? As soon as it receives an acknowledgement for a particular packet, it can flush everything before that, right. But then I need to make sure that I do not transmit anything beyond the end of that buffer. I might need to slow down and wait until I get acknowledgements, or just keep on retrying until I do that. Okay. So, ACK-NAC based approaches are fairly simple to implement, right, but they have these things that they require certain buffer sizes, you need to store the data until you get all the acknowledgements and so on. Okay. Another variant of this is something called credit based switching, right, which is once again trying to solve the same problem. What it is saying is, I do not want to wait for acknowledgements on every single thing, I want to give this transmitter some amount of credit or buffering, basically saying, okay, you can transmit so many things to me at one shot, right, and I will let you know at some point if something is going wrong. In this case, what it says is, this is the transmitter, this is the receiver, right. The transmitter currently has 2 credits from the receiver. Okay. So, what does it do? It can send 2 flits or 2 elements of data across, right. As and when each one is sent, the number of credits you can see over here reduces, right, and at this point the receive buffer is full and the number of credits has gone down to 0, which means that the transmitter automatically stops. Okay. On the receive side, as soon as it popped out this H and sent back 1 credit, that got updated over here. Okay. It popped out the B and sent back another credit, but this and this transmission of T happened at the same time, so the number of credits remains at 1 as far as the transmitter is concerned. Okay. And then afterwards this one sends back one more, so by this point you should see that the number of credits has gone back to 2. Okay. So, yeah, after this what you would see is basically that T would be sitting over here and then T would get popped off in this case, right. It's simplifying the ACK-NACK implementation, but if you think about it really, there is no NACK that's coming back over here. There is no negative acknowledgement saying I did not receive a particular packet. All that it's saying is you can continue to send packets and at least my buffer is not full, right. So I am reducing it to the simpler case where I am only talking about the buffer part alone, okay. Another variant of flow control is the so called on-off flow control. Over here you just have one buffer which basically says it has a on threshold and an off threshold. As long as I am below the on threshold, keep on sending data. The moment I go above the off threshold, stop sending data, wait, go into the stop mode and just stop sending data, okay. Simple because the signaling between two blocks is just two wires, right, stop and go, right. In fact, one wire with different states, or you could have multiple wires to indicate the different levels of the buffer, right. The point is all of these different techniques can be used in order to implement various forms of flow control. The most important thing to keep in mind is, although I said that you can benefit from a lot of the theory of networks, trying to implement those complicated network protocols on a chip is almost certainly a bad idea, because in software you can allocate buffers, you can store data, you can retransmit, you just have like some if statements over there. But in hardware all that translates into more and more gates, more area, more capacitance, more power consumed, right, more cost, much more than what it would be in the software. So that's why all of these different techniques are sort of going more towards a hardware friendly way of implementing things. Yeah. Because yeah, in principle you need not have an on threshold. You can basically say anytime I have data, send it, right. But effectively what it's saying over here is sort of the other way around. Let's say that incoming flits are pouring in, right, going in over here, right. If I fill up to get to this point over here, f off, right, above the off threshold, stop. So that's basically where the back pressure will go and say, tell the previous unit to stop. The problem is, let's say that I drop below that and immediately the other unit starts sending data again, right. Potentially I might end up with the situation where I am just sitting over here turning it on off to on off on off. Instead what we say is I will provide a slight hysteresis, right, let the other side clear out some data, right, to prevent this sort of jumping between stop and go continuously, right. So when I turn off the signal, I leave it off for a short amount of time so that the buffer gets time to clear a little bit, so that when I reactivate it, it can accept more data. It's not absolutely necessary, you could just have one threshold, it will still work, but you can potentially end up with that sort of bouncing state. I clear a data, immediately one new data comes in, once again I go into stop. So I am going on losing cycles each time that happens. So the last thing is some issues that come up in the concept in the context of understanding this. One of them is called deadlock. I told you already about deadlock, two things coming together at the same time. Usually that happens also in the case of circular dependencies, right. Let's say that 4 units or the ideal situation is 2 units trying to talk to each other, right. This is trying to send some data, the other one is trying to send some data back. This has already sent part of the data and filled up the buffer over here, so it can't continue sending the data, it is still stuck over here. This one is not able to, so B is not able to send the data because once again it is waiting for something that is coming from A, right. So deadlock can happen in that kind of situation. It can even happen in the case of the flit based routing, right. There are examples where you can show that it can lead to deadlock if you are not careful about how you do it. Live lock is a more interesting scenario, you don't want it to happen, but it's something that can actually come up in these kind of routing scenarios. In particular, there is one technique called hot potato routing. Hot potato routing essentially says somebody is passing you a hot potato, you don't have time to hold on to it, you just want to give it to somebody else as quickly as possible, right. So what is the switching strategy used over there? Each switch doesn't sort of wait for its neighbors to see which one is free, or rather whether the correct one there where it needs to go is free. It just looks around, whichever one is free, it sends it there. Okay. Hopefully over time it will make its way to the correct destination. It's not as bad as that, there is obviously some more to it, but the idea is that you don't need any local storage, you don't need buffering. The problem you can end up with is live lock, where packets keep going round and round the network without reaching their destination. Okay. And finally, starvation, we already talked about this in the context of priorities, right, in the bandwidth on a shared bus. You can just end up with some nodes that are not able to communicate. Why? Because of whatever, some aspect of the routing protocol that you chose. Okay. So these are all more serious issues that come up in the context of implementation of these things. There is a whole huge literature in the context of NoCs that you can go into if you are interested, but as far as we are concerned, we are stopping here with that.